Well, let's get cracking here. Okay, so Chemistry 111, we're going to continue on here with Chapter 1, and we're going to start by looking at some questions from Chapter 1. It says here, gold is a precious metal that is chemically unreactive. It's used mainly in jewelry, dentistry, and electronic devices. You think, that's one of the reasons why gold is so valuable, because it doesn't tarnish or it doesn't oxidize in the air. That's why gold jewelry is so valuable. Anyhow, it says here, a piece of gold ingot, which is like a little piece of gold with a mass of 301 grams, has a volume of 15.6 centimeters cubed, and it's asking us to calculate the density of the gold. So what we need is the formula for density. And if we back up to the last slide that we looked at in our last lecture, or one of the last slides, we saw this formula right here, that density is equal to mass over volume. So I'm going to copy that formula and bring it over here. And you need to have that formula memorized. Come on, here we go. There we go. There. All right. So density is equal to mass over volume. Now we can just plug our numbers in, because we know the mass of our gold is 301 grams. We know volume can be measured in centimeters cubed, and our volume is 15.6. So we plug in 301 grams, and we divide that by 15.6 centimeters cubed. You grab your calculator. I have a couple here on my desk. I'll just grab closest one, and I take 301 and I divide it by 15.6, and I get 19.3. So I have 19.3, and my units are grams per centimeter cube. So grams per centimeter cube, that is my density. Give me a thumbs up if you follow me on that one. Our first math problem of the semester, really. All right, good. Thanks, Anthony. Thanks, Hannah and Taylor. Perfect. Let's keep moving. Let's look at another question, still dealing with densities. And the question asks us, it says, the density of mercury, the only metal that is a liquid at room temperature, is 13.6 grams per milliliter. So that's a density. Calculate the mass of 5.50 milliliters of the liquid. There should be a period there. Well, we know that this is the volume, the 5.50 milliliters, and we can use the formula D is equal to M over V. But we want to solve it for M, and we can rearrange that formula by multiplying both sides of this equation by V. If we multiply this side by V, V is going to cancel, and if we multiply this side by V, we get the M is equal to density times volume, and you should be able to do that in your head. So we have our density, which is 13.6 grams per milliliter. We multiply that by our volume, 5.50 milliliters. You can see that the units of milliliters cancel because they're on the denominator and numerator respectively. And when we multiply all that spinach out, we get that the mass is equal to 74.8 grams. All right, so that's just a matter of rearranging the formula. The plain old formula, density is equal to mass over volume. And that is a formula that you must know when you step into the examination room. Let's move on from there. Let's talk about temperature scales for a little bit. Now, if you grew up in the United States, you're fully aware of the Fahrenheit scale, which is shown here on the right-hand side. But I grew up in Canada, and I'm used to using this Celsius scale. And another scale that we're going to use quite a bit in general chemistry class is the Kelvin scale, and they all have their place depending on the situation. Now, the Fahrenheit scale, we're not going to use that a lot in this class, except for when you're given a temperature in Fahrenheit, you have to be able to convert that temperature into degrees Celsius. Okay, you have to be able to convert from Fahrenheit into degrees Celsius. Now, if we look at the Celsius scale, you can automatically notice two really interesting points, 0 and 100 degrees Celsius. Well, 0 degrees Celsius is the freezing point of water, the point where water is converted from a liquid into a solid, and 100 degrees Celsius is the boiling point of water. This is the point where water is converted from a liquid to a gas. Now, the numbers of the freezing point of water and the boiling point of water in the Fahrenheit scale, personally, I think they're a little more difficult to memorize, 32 degrees Fahrenheit and 212 degrees Fahrenheit, but you should also have those in your cap as well. Something else that you'll find interesting is that 1 degree in Celsius is different from 1 degree in Fahrenheit. Okay, they have a different increment. There's a different amount of temperature in 1 degree of each. Whereas if we compare the Kelvin and the Celsius scale, you'll notice that if we go from the freezing point of water, which is 0 degrees Celsius, in Kelvin it's 273, but if we go up to 100 degrees Celsius, it's 373. That tells you that the increments for temperature in Celsius and Kelvin are identical. Okay, if my temperature increases by 1 degree Celsius, it increases by 1 Kelvin. Now keep in mind that Kelvin are not degrees. Okay, we don't call a Kelvin a degree. It's just a Kelvin. We have degrees Celsius, degrees Fahrenheit, but we don't have degrees Kelvin. They're plain old Kelvin, like Cher or Madonna, right? Okay, well, if 273 Kelvin is the freezing point of water, the scale on which the Kelvin temperature is based on something called absolute zero. And let me explain that to you right now. If you take matter and you cool it to the coldest temperature that it can attain, where there is essentially no molecular movement at all, the molecules are not moving, atoms aren't moving, electrons aren't moving, nothing is moving, that's called 0 Kelvin. Okay, that is also what we call absolute zero, and that is actually a theoretical temperature. Nobody's actually ever attained absolute zero. It is the lowest possible temperature that can be attained. Okay, and if we want to convert from Kelvin into degrees Celsius, you can see that all we have to do is take the degrees Celsius and add 273. Now here they're using 273.15. So technically this number is 273.15. But the rationale still stands. Okay? If I have 0 degrees Celsius being equal to 273 Kelvin, well, how would I convert degrees Celsius to Kelvin? All I'd have to do is add 273 to it. Okay? Notice the same thing here. If I want to convert 100 degrees Celsius into Kelvin, I'd add 273, right? 273 plus 100 gives you 373. And so the formula, again, for converting Kelvin into degrees Celsius into Kelvin is to simply add 273.15. Okay? Now, if we want to convert from degrees Celsius to Fahrenheit, that's a little more complex. What we would want to do then is we would take the temperature in degrees Celsius, add 32 to it, and multiply it by 9/5. Okay, that's the conversion factor that we use. You need to have this memorized as well. Now, you only need to memorize this formula because I'm also going to ask you sometimes to convert degrees Fahrenheit into Celsius. And you should be able to rearrange this formula that I just circled in blue. You should be able to solve that for degrees Celsius. Okay, so you should be able to say that degrees Celsius is equal to degrees Fahrenheit, subtract 32, multiplied by 5/9. So that's just a little quick exercise in algebra that I did there. Okay, isolating the degrees Celsius. So as you can imagine, I'm going to ask you to do all kinds of temperature conversions in this class. So with that in mind, let's get some practice on temperature conversions. This is a question that says, solder is an alloy made of tin and lead. It's used in electronic circuits. A certain solder has a melting point of 224 degrees Celsius. What's the melting point in degrees Fahrenheit? We just saw the formula that to convert, from Celsius into degrees Fahrenheit. We say degrees Fahrenheit is equal to degrees Celsius times 9/5 plus 32. If I back up here, right? Okay, so with that formula in mind, we're just going to plug in our numbers. All right, so let's do that. We're going to say we have our temperature in degrees Celsius. We put in 224 times 9/5, like that, and we're going to add 32 to it, like this. If you punch that in your calculator, following the correct order of operations. Now, I'm just going to go over this quickly because I was lecturing in another class the other day, and a student told me they didn't understand the order of operations. Has anybody heard of BEDMAS before? PEDMAS. Has anybody heard of this before? Yeah.
PEMDAS.
Okay. Yeah. Good. All right. PEDMAS. Okay. So BEDMAS or PEMDAS, whatever you want to call it. Okay. It means brackets and exponents first, right? Division and multiplication and addition and subtraction. So that means you're going to punch this in your calculator first, then you're going to add 32 to it. So if we take 224, 224, we multiply by 9, divide by 5, we get 403.2, and then we add 32 to it, and we end up with 435 degrees Fahrenheit. So 435 degrees Fahrenheit is our final answer. Now, for any of you who watched all of my videos or who have studied in a science class before and know all about, if you know all about significant figures, you might be wondering, well, what's the significance here about significant figures? You know, I guess I should include degrees Fahrenheit here. Anyhow, I'm going to talk about that even more a little bit later on. That's going to be part of our lecture tonight. So we'll get into that more later on. But let's just practice our conversions more. Here it says helium is the lowest boiling point of all elements at 452 degrees Fahrenheit. Convert this temperature to degrees Celsius. Well, again, we went over this earlier. We said the formula to convert from Fahrenheit to Celsius was degrees Celsius is equal to the temperature in Fahrenheit, subtract 32, multiplied by 5/9. So if we punch in some numbers here, we have 452 minus 32, like that, so it's 420, multiplied by 5/9, so we say 452 minus 32 times 5 divided by 9, and we end up with 233 degrees Celsius as being our temperature in degrees Celsius, just like that. Give me a thumbs up if you feel like you could do these last two questions. Like, I can convert, just let me memorize the formula, and away I go. Away I go. Great, thanks, Kristen. All right, perfect. Well, let's move on from there. Let's try one more. Again, I don't like to use the word easy in chemistry class. I don't think that's fair. But I'd say, converting between Celsius and Kelvin is one of the easier things for my students to do. It says here, mercury, the only metal that exists is a liquid at room temperature. We're really obsessed with the mercury here, aren't we? Melts at 238.9 degrees Celsius. Convert its melting point into Kelvin. Okay, let's see here. So we know that the temperature in Kelvin is equal to the temperature in degrees Celsius plus 273.15. Most of the time in our class, you can just round that off to 273. But if you want to add the 273.15, there's certainly no problem with that. So we get 238.9 plus 273.15. And we get that our temperature in Kelvin is equal to 512.1 Kelvin. And there we go. That's all there is to it, like that. All right, let's go over this slide. I mean, this is something that you could read in the textbook. It's kind of one of those human interest stories, if you're a scientist anyway, talking about why do people care about conversions. As a chemistry teacher, what I would say, is why a chemistry student who wants a good grade should give a darn about units. You notice that I'm always including the units on everything, especially in those density problems. And you're going to see moving forward, we're going to use units and conversions. And the reason why conversions are important is if you look at the story of the Mars Climate Orbiter, which went into outer space a long time ago. I mean, it was over 20 years ago. But this thing cost $125 million, and it burned up, in the lower atmosphere of Mars, as is my understanding. And the snafu, or the error that occurred, was simply based on the difference in conversions, or the different units that were used between British scientists and American scientists. Okay, they assumed that 1 pound was equal to a Newton or something like that. I don't remember the entire story, but basically, they wasted $125 million just because they didn't do a conversion correctly. So something to think about, if you're ever stuck, thinking like, why do I even need to know this? Well, it's really important in chemistry class. All right, let's talk about scientific notation kind of quickly, because this is something that I'm sure most of you saw in high school. But let's say we have a really big number, like this big number here, or right? There's a really big number or a really small number. Well, the news is in general chemistry class, you're going to see all kinds of really big numbers and you're going to see all kinds of really small numbers all the time. They're coming up in chemistry class. So if I have this number here, I mean, I'm the first guy that if somebody asked me to write that down, I'd probably be the first guy to make a mistake on one of those zeros. I'd miss one or I'd add an extra or something like that. So if I want to use that number in an equation, the best thing to do would be to express it in terms of scientific notation, right? It says here the number of atoms in 12 grams of carbon is 6.022 times 10 to the 23, or this big number that I have highlighted in yellow. How do I get from here to here? Well, the way I do that is I'd start here at the ones place and I go 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So I multiply that by 10 to the 23rd power, this number, 6.022, and I'm going to end up with this number. But it's a much faster way to express that really large number. Similarly, if I want to express a really small number, I'm going to move the decimal place to the right-hand side. Look, 10 to the negative 1, 2, 3, 4, 5, 6, 7, 8, whatever, all the way down to, oops, 23, like that. So I have 1.99 times 10 to the power of 10 to the negative 23. All right, so what we do is we use n, where n represents a number between 1 and 10, and n is always going to be a positive integer, and we can use 10 to the power of a positive or a negative number to represent a number that's greater than 1 or a number that's less than 1, respectively. Give me a thumbs up if you follow me on scientific notation and what the concept is before we look at a couple of problems. All right. I didn't make it through counting, 23 spaces to the right, did I? Okay, I lose my patience with this kind of stuff, Another thing that you want to remember moving forward is you need to know how to use the scientific notation function on your calculator. And if you're unsure how to do it, be sure to Google it, because I guarantee you that there's going to be some kind of tutorial on YouTube of somebody, trying to get likes or something, of showing you how to use your calculator and the scientific notation function. Well, let's convert some numbers to scientific notation. I have 5,687.72. How would I convert that into scientific notation? Well, I'm going to move the decimal place to the left-hand side 1, 2, 3 places. So this number would equal 5.68772 times 10 to the third power, right? What's 10 to the third power? If you take 10 and you cube it, it's 1,000. If I multiply this number by 1,000, you know that the decimal place is going to move over, what, 1, 2, 3 places, right? And you would end up with 5,687.72. That's the concept of scientific notation. Let's try the next one. The next one is a number smaller than 1. I'm going to move the decimal place to the right. How many times? 1, 2, 3, 4, 5. If I do that, I get 6.42452 rather times 10 to the negative 5. And now I've expressed that number in scientific notation. Now, if you have to add or subtract numbers that are in scientific notation, there isn't really a simple way to do it, except for to make sure that each quantity has the same exponent. Okay, like let's say we wanted to add these two numbers here. Since one of them is to the power of 4, the other one's to the power of 3, you've got two options. You can either convert this one to the power of 3 or this one to the power of 4, as is shown here. Once the exponents are both identical, then you can just tally up this part here, and there you go. 4.31 plus 0.39 is 4.7, and the exponent isn't going to change. BTW, by the way, the leading part, okay, now correct me if I'm wrong, but the leading part of these numbers here, this is called the mantissa, or the mantissa, what it's called anyhow. Anyway, let's move on from there. And let's take a look at some more rules that deal with scientific notation. We'll go over these kind of quickly. The rules for multiplication and division. When you're multiplying two numbers that are both written in scientific notation, what do you do with their exponents? All right, if I want to multiply these numbers here, What do I do with the exponents, the -5 and the +3? The answer is you add them together. So you're multiplying these two numbers, and you're adding these two exponents together. So if I have -5 plus 3, what do I get? I get -2. Now, if we just take a quick, look over at my screen here. So let me just stop presenting for a second, and I'm going to pray that you guys will be able to see what I'm doing here. Can you see my calculator? Okay, kinda. I don't know. Is it backwards? I don't know. Anyhow, if I punch this in, can you see it? Okay. Look, if I have my calculator here, the way that it works on my calculator is I type in 4.0, then I use this double E button, okay? And that gives me an exponent. Now you can see there's an exponent up there and there's nothing written in it. So I'm going to put 5, and then I press the negative key, and then it looks like this, 4.0 times 10 to the -5. I press the multiplication, right? And then I put 7, okay? Then I'm going to press the double E button again. This one here, this looks like double E. I press that. That brings up the exponent. There's nothing there. I'm going to put 3 in there. And then I'm going to press enter. And what I get is 0.28. So it says 0.28 is my answer. If I want that in scientific notation, all I have to use is the scientific notation function. So on my calculator, you press second function, 5, and then look what it says, 2.8 times 10 to the -1. So it gives you the entire answer in scientific notation. Very powerful tool for you to use. So I'd recommend learning how to use the scientific notation function in your calculator if you've never done it before. Okay, make sure you learn how to use that. It'll save you a lot of hassle. Okay, if we're dividing, however, we divide the mantissa, so I would divide 8.5 by 5. But what do I do with the exponents? I subtract them. So I would take 4 minus 9, which would give me -5. But again, it's much easier to just punch it into your calculator. All right, let's talk about what are called significant figures. Significant figures are the numbers that count, okay? When we're doing any kind of calculations. They're numbers that have meaning. And if you're like, well, how could a number be meaningless? Well, if you're using a ruler to measure something in inches, okay? And this is just kind of an off-the-cuff explanation. Let's say you catch a fish and you measure it and you say, hey, this fish is 11 inches long. Somebody would say, hey, that's cool. Hey, man, I caught a fish. It was 11.5 inches long. Oh, neat, neat. Hey, I caught a fish. It was 11 and 13/16 inches long. Okay, you're getting kind of specific there. You're not going to believe it, man. I caught a fish and it was, 11 inches and, 3/128ths of an inch. There's a point there where it gets crazy, where numbers have no meaning. And without me getting into any more of the details than that, we just have to realize that digits carry meaningful contributions to our measurements. So we have to learn which numbers have meaning and which ones don't. Well, let's learn the rules for significant figures. The first rule is that any digit that's not a 0 is significant. Pretty simple rule, right? Anything that's not a 0, so 1, 2, 3, 4, 5, 6, 7, 8, 9, those are all significant. So if I have this number 1.234, I don't see any zeros, so everything's significant. I have 4 significant figures, 4 significant numbers in there. If you have a 0 that's sandwiched in between non-zero digits, it counts as significant. Let me give you an example. It says here you got 606 meters. Since the 0 is sandwiched in between 2 6s, it counts. So I have 3 significant figures. Let me ask you a question. If I had the number 50,003, could anybody tell me how many significant figures there'd be in that number? Thanks, Hannah. The answer is absolutely, there'd be 5, right? Because any number that's sandwiched between a non-zero is significant. And from the first rule, anything that's not a 0 is significant. That means that all of these numbers are significant, and I would have 5 significant figures in that number. So let's move on to, into numbers that aren't significant. If you have zeros to the left of a non-zero digit, they are not significant. Sometimes we call those leading zeros. You can write that in here. Sometimes we call these leading zeros. Zeros that begin a number, they are not significant. So if I have 0.08, since these two zeros are to the left of a non-zero, right? Because 8 is a non-zero, excuse me, I only have one significant figure in that number. Right, let me ask you a question. What if I had this number? What if I had 0.000303? Can anybody tell me how many significant figures there would be in that number? Exactly, there'd be 3. Because the leading zeros are non-significant, I do have another 0, but it's sandwiched in between 2 non-zeros. And so there would be 3 significant figures there. All right, if the number is greater than 1, then all zeros to the right of a decimal point are significant. You can see that we have a decimal point here in this number, 2.0. That 0 is to the right of the decimal point, so we have 2 significant figures. If I had 2.000 milligrams, how many significant figures would there be in that number? Could anybody tell me? Yeah, exactly. There'd be 4, right? Because I have 3 zeros after the decimal place. They're all significant. So I have a total of 4 significant figures in that number. If the number is less than 1, then zeros that are at the end and in the middle of a number are significant. So if you have a number less than 1 and you've got zeros after non-zeros, they are considered significant. Okay? Nothing more than that. So those are the rules that we need to know what is a significant figure and what isn't. There's one more rule, and I'm going to go over it with you in a little bit, but just bear with me because we're going to try some practice first, okay? One more rule, and I'll get to that in a few minutes. Okay, let's talk about addition and subtraction, multiplication and division, and their implications in terms of significant figures. Well, we'll start with addition and subtraction. When we add or subtract numbers, the answer, our final answer that we get from our calculator or our brain, cannot have more digits to the right of the decimal place than any of the original numbers. Okay? That means that the number of decimals you have in all the numbers you're adding up, whichever one has the least number of decimals, that's the one that governs how many decimals you have. If you're trying to add up these two numbers, the first number has 1, 2, 3 decimal places. This number has 5 decimal places. What's a lower number, 3 or 5? 3 is a lower number. Therefore, your final answer can only have 3 decimal places. I'm going to take this and punch it into my calculator, 89.775. I recommend following along. You have 2.54, 236. I end up with this big number. I get 92.31736. This is what my calculator is telling me. It's not the right answer, though, because I can only have 3 significant figures. These last 2 numbers here, those are not significant. My answer should be 92.317. That's the actual answer. Let's look at the next example. This number has 1 decimal place. This number has 1, 2, 3, 4, 5, 6, 7, 8 decimal places. Could anybody tell me how many decimal places will there be in my final answer? And it's not a trick. Yeah, thanks everybody. The answer is 1. So if I take all of these 2 numbers and I add them together, you find that I still get 92,157.1 as my final answer because I can only have 1 sig fig. All right, multiplication and division I think is even a little more intuitive or maybe a little faster to learn than addition and subtraction. The answer is this. When you multiply numbers together, whichever number has the least number of significant figures, that's how many significant figures you have in your final answer. Same thing for division. If I multiply these 2 numbers, 4.51 and 3.6658, the first number, 4.51, has 3 significant figures. The second number has 5 significant figures. That means my answer can only have 3. So when I punch that into my calculator, let me do it right now. If I take 4.51 multiplied by 3.6658, I end up with this number. Look, this is what my calculator tells me. 16.532758. But the calculator isn't smart enough to give me the correct answer. My final answer can only have 2 decimal places, so all of this is now insignificant. It is not significant. So my answer is actually 16.53, like that. Oh shit, what the hell am I talking about? I'm mixing up multiplication and division and addition and subtraction. Anyhow, my final answer, sorry, should only have 3 sig figs. So all of this is going to be insignificant, and my final answer is 16.5. Sorry about that. I got too many things on my mind here. I won't mess up on this one. The next one, I have 2 sig figs here in my numerator, and I have 6 in my denominator, so my final answer can only have 2 sig figs. So let's punch that in our calculator. 6.8 divided by 11.0252. I get this huge number. I'm not going to write the whole thing out, but my final answer, it says 0.61676, blah, 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 like that. My final answer can only have 2 significant figures. So that means it can only have these 2 decimal places. But guess what? Since I have a 1 here and the number that follows it is a 6, I have to round that 1 up to a 2. 0.62 is my answer, like that. And we'll talk more about rounding numbers in a little bit. All right. Actually, I don't even know if I have that in there. Do you guys know the rules for rounding numbers? Everybody know the rule? If you have 0, 1, 2, 3, 4, the number stays the same. And if you have 5, 6, 7, 8, 9, you round up. Okay, so round up. And here you have stays the same. All right. Somebody's asking me, 6.8 is only 2 significant figures. That's correct. But this number here, 0.62, only has 2 significant figures, right? The leading 0 here, okay, since the number is less than 1, we have a leading 0, it is insignificant. So only these 2 digits are significant. Does that answer the question? Okay, great, perfect. All right, there we go. So we've gone over the rounding rules, we've gone over addition and subtraction, multiplication and division, significant figures. Well, let's talk a little bit more about significant figures. Specifically, I want to talk about what are called exact numbers. Now, exact numbers are something that we're used to using in our everyday life. Let me explain. Exact numbers are numbers that have an infinite number of sig figs. And you're like, what? An infinite number of sig figs? How is that even possible? Well, let's pretend, we're talking about who's online in class this evening. If I look at the class list, we have about 19 people in class right now, okay? The attendance is 19. There is no way the attendance could be 19.1 or 19.2 or 18.9. It's 19. It's an exact number. There is no question about it that we have 19, and we call that an exact number. It's when we used to count something, okay? So that 19 is known with an infinite amount of significance. So it has an infinite number of sig figs. All right. Let me give you another example. If a chicken lays eggs, a chicken will lay 2, 3, 4, 1 egg. A chicken won't lay 3.8 eggs. It doesn't happen. So we're used to exact numbers all the time. There's 31 days in July. There's never going to be 31 and a half or 30 in an hour or anything like that. There's always the same number of hours in a day, same number of seconds in a minute, etc., etc. So if we had 3 lengths and we wanted to take the average of these 3 lengths. Now, what's funny about these lengths is there's no units, is there? But anyhow, let's say we measured something 3 times and we got these 3 measurements and we want to take the average of them. If I tally up the numerator, okay, I should only have 2 decimal places because each one of these numbers only has 2 decimal places. I get 6.67. Since 3 is in the 0, 1, 2, 3, 4, the 7 is going to stay. So I get 6.6, sorry, I haven't, sorry, and then I divide by 3. Sorry, I'm getting ahead of myself. Sometimes my brain works faster. My mouth works faster than my brain. Anyhow, so if I take 6.64 plus 6.68 plus 6.7, like that, If I tally all that up, I'll write it over here. You get 20.02. Okay, and you want to divide that by 3. All right, now the 3 is an exact number because it's 3 measurements that you took. You can't measure something 3.5 times or 3.1 times. It was exactly 3 times. And so since when I divide this by 3, since I can only have 2 decimal places, okay, my number or my final answer is going to be 6.67. All right, because 3 is an exact number, I'm not going to round it up to 7 to one significant figure. Give me a thumbs up if you just follow me on the concept of an exact number. An exact number. All right, good. Perfect. Well, let's move on from there. Exact numbers, good stuff. And let's try some quick practice here. And this is where we're going to get into that one additional rule. I'll just throw it out there to my students. Can anybody tell me how many sig figs there would be in A? Not a trick question. Yeah, there's 3. There's no zeros in there anywhere, so that number has 3 sig figs. What about B? How many would there be in 3? Or how many would there be in B? In B, there's 3, right? There's 3 sig figs in this one as well. You have a 0, but it's between 2 non-zeros. Therefore, that number has 3 sig figs. What about C? Yeah, in C, there's 3 sig figs as well, right? Because the leading 0 is not significant, so there's 3 sig figs here. In D, I'll do D for you. D has 2 significant figures because all leading zeros are insignificant. Let's try E. Can anybody tell me how many are in E? Yeah, there's 4, right? Because the trailing 0 after a decimal place is significant. So I have 4 significant figures here in my mantissa. I don't worry about this part when I'm determining the number of sig figs. And here's the last one. Now this one I'm not going to ask you because that might even be considered a trick question. If you've read our textbook, which I trust you all have, and you look at a question like this, it'll say how many sig figs? The answer is it could be 1, it could be 2, it could be 3, it could be 4. It's actually ambiguous. We don't, yeah, exactly. See, Hannah wrote that out. I see that Anthony wrote the same thing. They both said, well, we don't know. Okay, nobody knows because we're not given enough information. Okay, we don't know if these zeros are significant or not. A way that we could turn 7,000 milliliters into a number that has 4 significant figures would be to do this. If we wrote it as 7,000 decimal milliliters, then there would be 4 significant figures. How could I report 7,000 milliliters to 3 significant figures? If I wrote 7.00 times 10 to the 3, right, that would be equal to 3 significant figures. And if I wrote it as 7.0 times 10 to the 3, then it would be 2 significant figures. And if I wrote it as 7 times 10 to the 3 milliliters, then it would have only 1 sig fig. So that's how you could express it using either 1, 2, 3, or 4 significant figures. So kind of a little trick there. All right, well, in the interest of time, and because of our snow day, I'm not going to do this entire question, but we'll try a couple of them here. We'll start with A. The question is, we want to do some arithmetic and we want to report the final answer to the correct number of significant figures. If you grab your calculator right now and you punch in 11,254.1, 54.1, and you add 0.1983, you get this big number. I'll write it out here. You get 11,254.298. My question is to you, how many decimal places can I report this final answer to? Exactly. I can only report it to 1 because this is an addition problem. This number has 1 decimal place. This number has 4. Now, since it's a 2, and remember that if we have the number that follows it is a 5, 6, 7, 8, or a 9, then you're going to round up. Round up. And so this number would become 11,254.3 would be your final answer, like that. Okay, Let's try a multiplication problem. Let's go all the way down to C. If I have 8.16 meters and I multiply that by 5.1355, I get this big number. I get 41.90568 meters. I forget my units here. Anyhow, meters. How many significant figures should there actually be in this answer? Not a trick. Exactly. You're all correct. The answer is there should only be 3 sig figs, shouldn't there? Let me just fix this up a little bit. There we go. So this number would actually equal 41.9 meters. Okay, we'll try one more. We'll try the one that involves scientific notation. You could get some practice in this. I mean, you got a couple options. You can punch it in your calculator, or you could convert both of them to having the same exponent. So you could say 2.64 times 10 to the 3 plus 0.327 times 10 to the 3 centimeters. I'm leaving my units out. That's an option. I don't like that option. I say just do it in your calculator, and then figure out the correct number of decimal places, right? You should only have 2 decimal places to the power of 3. So when you punch all that in your calculator, you get 2.94, no, 2.97, 2.97. You get 2.967 times 10 to the 3, but you can only have 2 decimal places, so it equals 2.97 times 10 to the 3 centimeters would be your final answer. All right. This is just a review of math and skills that I'm sure many of you learned in high school and whatnot. But let's switch gears again. We do that a lot in the first couple chapters, and we're going to talk about accuracy versus precision. We just want to get these definitions out of the way. I find that the words accuracy and precision are used all the time in everyday parlance, but sometimes they are used incorrectly. Somebody will say accurate when they mean precise. Somebody will say precise when they mean accurate. So as a Chemistry 111 student, you need to know the difference between accuracy and precision. Let's cover that right now. Accuracy has how close you are to the true value, right? If you're trying to hit a bullseye, okay, and let's say you throw one dart, for example, at a dartboard, and you hit it right in the center. You'd say, man, that was accurate. That was really accurate. But the thing is, it doesn't tell you anything about precision. If you're like, what? It's not precise? No, not necessarily, because precision, in order for something to have precision, you've got to have a set of measurements. So what do you mean by that, Mr. Dion? If you threw a bunch of darts at the bullseye, and they all were very close to the bullseye, you could say, hey, all of those are pretty accurate. They're all pretty close to the bullseye, but they're also precise because the set of measurements are in agreement with each other. Let me show you another time you could use precision. If you threw all the darts and they ended up way far away from the bullseye, but they were all grouped together, wasn't very accurate, was it? But they are precise. You're like, what? Yeah, they're precise because the measurements are all close to each other. And if you look at the last scenario here, you just have like a scattered, the shots went everywhere. I think the dart thrower maybe had a blindfold on, or they had too much to drink or something. And you could say that these shots, or these these shots, you could say none of them are accurate, none of them are close to the bullseye. It's definitely not precise. So the difference between accuracy and precision, that might be worth the value of, say, one multiple choice question on your first exam, but you need to know the difference between precision and accuracy. Well, let's move on again to what's called dimensional analysis, and I'm sure that many of you learned dimensional analysis in high school, or maybe another college, or maybe even in junior high. And dimensional analysis is going to be our preferred method of problem solving in this class. Okay, we're going to use dimensional analysis all the time. And the reason why we use dimensional analysis is because many calculations can be done kind of in your head, but you're going to find that, as the course progresses, we get into more and more calculations that can't just be done in your head. You will need to get a calculator out. And so if we use the dimensional analysis method of solving problems, it's going to help us to avoid making mistakes And it's going to help us be able to solve problems when we don't even know what to do. We can at least get it set up and then try to figure our way through the problem. So what we're going to do is we're going to use this method. Step one, we're going to determine which unit conversion factors are needed. What do you mean by conversion factor? Well, we use conversion factors in our life all the time. 7 days in a week, 4 quarters in a dollar, right? 10 dimes in a dollar. I don't know. 30 days in June. Anyhow, we use conversion factors all the time. And another note that's really important is we're going to carry our units all the time through our calculations. It's a knee-jerk reaction for students oftentimes to want to avoid using units. They say, hey, they're just a pain in the neck to write them down. I don't like doing it. I don't like writing out units. Well, I can tell you right now that I've seen students who got a B in this class when they should have had an A, and the only reason why that happened is because they refused to use units and they would make silly mistakes. It's happened to me if I don't use units, so I always try to use units now. And if all the units cancel except for the desired units, then you can say, hey, I solved the problem correctly. All right. Now, if you're like, I'm not even sure what you're getting at here, Mr. Dion, like, how are we going to use this? Well, I can promise you this, that if you practice dimensional analysis, the more you practice it, the better you'll get at it to the point where you will literally master it. Well, let's get into what dimensional analysis is, and the best way to do just about anything in chemistry is to try it, okay? Is to try a problem. It says here, a person's average daily intake of glucose, which is a form of sugar, is 0.0833 pounds. What is the mass in milligrams? And here is our conversion factor. This is the conversion factor. We know that in 1 pound, there's 453.6 grams. Now, again, what we want to do is we want to cancel out the units of pounds and we want to end up with milligrams. That's our goal. You can even write it down. You can say, I want to get from pounds to milligrams. I want to get there somehow. Let's start by writing down what the heck we know. And we know that the amount of glucose that's consumed is 0.0833 pounds. Okay, what can I multiply this by to get rid of pounds? Well, I have a conversion factor right here, and I know that in 1 pound, there is 453.6 grams, like that. Okay, 456.3 grams. Already, you see that pounds are canceling out, and you would be left over with grams. Is our problem over? Absolutely not. If you studied and read our textbook, you would probably know how many milligrams are in 1 gram. Could anybody tell me how many milligrams, milli, are in 1 gram? Exactly. Thanks, Anthony. Thanks, Mackenzie, Christina, everybody. Exactly. There's 1,000 milligrams. 1,000 milligrams in 1 gram. Okay? In 1 gram, there are 1,000 milligrams. And those are exact numbers because it's a conversion factor. So, when we multiply this conversion factor by, oops, I put them in the wrong spot. Nobody corrected me. So there we go. So we know that in 1 gram, we have 1,000 milligrams. That's better. That's more like it. Okay. I like that. Let me clean that up. It's ugly. Let's see. In 1 gram, we have 1,000 milligrams, like that. There we go. Now you can see that grams cancel, and we're left over with the units of milligrams. So if you punch all this into your calculator, you end up with, let me see here, 0.0833 times 453.6 times 1,000. We end up with this. Now that number has 7 significant figures in it. Could anybody tell me how many significant figures should there be in my final answer? The answer is 3, because I only start out with 3 significant figures in this number, right? 0.0833 only has 3 sig figs in it. And we can assume that our conversion factors have an infinite number of sig figs. And so how would I report this number to three sig figs? I'm going to have to convert it to scientific notation. So I'm going to say that this is equal to 3.78 times 10 to the 4 milligrams. That's the number in scientific notation, right? I rounded this 7 up to an 8 because it's followed by an 8. All right? Somebody's asking me about cubing it. This question has nothing to do with cubing it. Usually when you cubing something, most of the time in a dimensional analysis problem is when you're involving volume. So let's look at an example where we would have to cube something. Let's move on and try another problem. It says the average adult has 5.2 liters of blood. What's the volume of blood in meters cubed? Before we answer this, let me back up and mention one thing that I forgot to do, okay? And that is this conversion factor here. If there's a conversion factor that's like pounds to grams or feet to inches or whatever, conversions between, imperial units and metric system, I will always give you that. If it's a conversion factor within the metric system, what? 10 centimeters in a decimeter, 100 centimeters in a meter, 1,000 meters in a kilometer, 1 gram is 1,000 milligrams. Those you're going to have to know. So this one you would have to come up with off the top of your head. This one I would give you. Okay? So with that in mind, let's see if we can solve this problem. And there's no conversion factor given to us. So we kind of have to know how to do this one. And it says you start it with 5.2 liters of blood, and you want to convert that into meters cubed. So you need to get from liters to meters cubed directly. Now, even if you don't have the number of liters in a meter cube memorized, we can still solve this problem, okay? Because I know how many centimeters are in a meter. I know that in 1 meter, there is 100 centimeters. Another conversion factor that I know is that in 1 liter, there is 1,000 centimeters cubed. So I can use these conversion factors to help me get from liters to meters cubed. Let me show you how you would do that. We have our 5.2 liters. I'm going to use this conversion factor first. I know that I have 1,000 centimeters cubed in 1 liter. Okay. Now, if I was to multiply all that out, my liters would cancel, and I would have my volume in centimeters cubed. That doesn't really help me a whole lot because I want my volume in meters cubed. But I also know that in 1 meter, I have 100 centimeters. Now, centimeters cubed and centimeters don't cancel. But if I cube this entire thing, right, if I cube that entire thing, then I'm going to get 1 meter cubed over 100 centimeters cubed, or sorry, 100 cubed, so 100 to the power of 3, which is equal to 1 times 10 to the 6th centimeters cubed. And we could write that out. If you're not following me, 5.2 liters times 1,000 centimeters cubed over 1 liter multiplied by 1 meter cubed divided by 1 times 10 to the power of 6 centimeters cubed, like that. Now you can see that the units of liters cancel, centimeters cubed cancel, and I'm left over with meters cubed, just like that. Now remember, since these are conversion factors in metric, they have an infinite number of sig figs, right? This conversion factor is an infinite number of sig figs. They are exact numbers, right? This is infinite and this is infinite, but here I only have 2 sig figs, and so my final answer can only have 2 sig figs. When you punch all of this into your calculator, you end up with 0.0052 meters cubed, which is a perfectly acceptable answer. There's nothing wrong with that at all, but I could convert that into scientific notation by moving the decimal place over 1, 2, 3 places. Then I get 5.2 times 10 to the negative 3 meters cubed. Either one of those would be perfectly acceptable. All right, give me a thumbs up if you follow me on that one. All right, good. Well, in the interest of time, since we're really running out of time now, I will not do I'm not going to solve the next two problems because those are solved in the next problems because they're in the solved in the videos that I posted in the announcement or in the email. I think they're in both. I think I sent an email and I also posted an announcement. Good, Anthony. I'm glad you're finding this cool. So what I want to do now is we're going to take a short break. Let me just stop recording here.